Section 2.6 gets at this idea of transformation of graphs. It's something we're going to plant on for 2 videos, actually. Today we're going to do it generally, and tomorrow we're going to make it more concrete with specific functions. We're going to look at how we can change the graph of a function, how we can move the graph of a function around. And as we do, there's 2 parts that we change. We change either the x or the y, or usually both. Now, changing the y is easiest, so we're going to look at that first. We're going to look at how the y changes with just the simple function that we're going to consider. The function f of x equals x. And if we graph f of x equals x, we should know it has a y-intercept of 0, a slope of 1. And so if we put 3 key points on here, the first one's going to be at 1, 1, 0, 0 is the second one, and the third one would be at -1, -1. And we're going to look at what happens when we take the function f of x and we add a number to it. Maybe we'll add 2 to the function. Well, the function used to be just x, and we said we were going to add 2 to it, so now it's x plus 2. And we're going to look at how this changes the y coordinate. Now, we should know that x plus 2 has a y-intercept at 2 and a slope of 1, so it's going to go something like this. And so we're looking at how y changes. We're going to keep the same x's we had before. So when x is 1, 1 plus 2 is 3. So we have 1, 3. When x is 0, 0 plus 2 is 2. So we have 0, 2 on the graph. And when x is -1, plugging -1 into the function, -1 plus 2 is a positive 1. And I want to notice how these x's, the x's we kept the same. The x's we kept the same at -1, 0, and 1. But we now have new y values. The y value of 1 has increased to 3. The y value of 0 has increased to 2. The y value of -1 has increased to positive 1. What does this mean for us? How are all these y values changing? What you should notice is what we've done is we have always added 2 to the y. Keeping the x the same, what we have done is we have added 2 to the y. So I want to notice adding a number to the end of a function adds that number to the y coordinate, which we might expect. I'm going to do a little similar exercise. But this time we're going to multiply our function by 2. We're going to take 2 times f of x. Now remember, f of x was just x, the simple function. So now we're going to multiply x by 2, and we now have 2x. Let's look at how that changes our graph. Well, we should know that 2x has a y-intercept of 0 and a slope of 2, so we know the graph is going to look like this. And if we plug in our known values of -1, 0, and 1, we're going to have new y values. When we plug 1 in, 1 times 2 is 2. We have 1, 2 on the graph. When we plug 0 in, 0 times 2 is 0. And when we plug -1 in, -1 times 2 is -2. And so I want to notice that while we kept the same x values again, -1, 0, and 1, the y values have changed. The y value that used to be -1 is now -2. The y value that used to be +1 is now +2. And the y value that originally was 0, whoops, wrong 0, the y value of 0, is still 0. And as you might guess, we're multiplying here because we multiplied the function by 2. You can tell we also multiplied our y values by 2. So that's what happens here. If the function gets multiplied 2, we multiply the y by 2 as well. And we're going to see this pattern no matter what type of function it is. If we multiply the function by 2, we multiply all the y coordinates by 2 as well. So that's kind of how we could change the y coordinate, kind of like we'd expect. Multiplying by 2 multiplies by 2. Add 2 increases by 2. Just what we expect with the y values. We're going to do a really similar exercise with the x values and look in part B how we can change the x values. And again, we're going to consider the same function, f of x equals x. And again, we should know that's a y-intercept of 0, 0, 0. And then we've got the point 1, 1, and negative 1, negative 1. And again, we're going to do the same thing. We're going to manipulate the function, but we're going to manipulate the part of the function that has the x in it. So we're going to keep the y values the same this time. This time we're going to keep y values of negative 1, 0, and 1. And we're going to look at how the x values change. So first we're going to find f of x plus 2. Notice we've added 2 inside the parentheses. Now the function really looks much the same. The x has been replaced with x plus 2, but that's the whole function. And so it's going to seem quite boring at first until we really look at what's happening. We know we've got a y-intercept of 2 and a slope of 1. However, this time we're going to keep the y values the same. So when the y is 1, we might even have to do a little bit of algebra. We're saying 1 equals x plus 2. Subtract 2 from both sides, and we find out that x is negative 1, 1. When the y value is 0, you can tell by looking at the graph, or by putting 0 equals x plus 2 and solving, we get when x is negative 2, y is 0. And you might notice the pattern will come up here and say instead of 0 equals, the other y value we want is when negative 1 equals the function, keeping the y value the same. Subtracting 2 from both sides, we find out that x is negative 3, negative 1. So again, we've kept the same y values in this problem because we want to see how x changes. Notice our x's went from 1 to negative 1, from 0 to negative 2, from negative 1 to negative 3. When we add 2 to the x-coordinate, it seems our graph actually has subtracted 2 from each x-coordinate. Notice this is different than the y's, which did exactly the same thing. Here the graphs are going to do the opposite, and we subtracted 2 from the x-coordinates. So it kind of feels backwards with the x. We see plus 2, so we subtract 2 from our x-coordinates. Similarly, if we multiply the x-coordinate by 2, replacing the x with 2x, we get 2x. And that looks much the same as what we did the last time, but again, this time we're going to be really interested in looking at what happens to the x-coordinates when we keep the y-coordinates the same. Well, our y-coordinate of 0, 0 is probably the easiest to keep track of. It's still at 0, 0. A y-coordinate of 1, though, if we make 1 equal to 2x and divide both sides by 2, we see the x-coordinate is 1/2 when the y-coordinate is 1. Similarly, if we do a y-coordinate of negative 1 and divide both sides by 2, we find out that x is negative 1/2 when y is negative 1. So notice from the original graph, again, we've kept the same y values and looked at how the x values changed. The x values went from 1 to 1/2, and from negative 1 to negative 1/2, and from 0 to 0. Notice this time, instead of multiplying the coordinate by 2, This time what we've done is we have gone through and we have divided the x by 2. And this kind of feels weird and different. With the y values, exactly what we expected to happen. When we add a number, we add to the y coordinate. When we multiply a number, we multiply the y coordinate, just like we expect. The x's are much the opposite, because the x's are affecting the input. What they do is they move the point of reference. They move the input. What's happened is the background actually moves what we expect. And so if you could visualize example 1 here, the background, the grid has moved right to. The graph stayed in the same place. And so when the grid moves right to, it gives the illusion the graph or the line has moved left to. And that's kind of what's happening with the x values. You see the opposite of what you expect to happen. And so to help us see that opposite, we come up with our translating rule here. Really generally, if y equals some number times the function plus a number, and then inside the function we multiply and add. So y equals a times f of cx plus d, adding b to the whole thing. The stuff outside of the function affects the y coordinate. To get our new y coordinate, we're going to call that y prime, our new y, what we do is we say we take a times y, notice the y replaces the f of x, plus b. It does exactly what we expect it to do. This is going to be an essential element for today and tomorrow's lesson. Y prime, the new y, we take a times the old y plus b. The x stuff all comes from inside the function, how the inside is being manipulated. And the inside is backwards. So it's not actually going to give us the new x, it's going to give us the old x equals the cx plus d. But this time the prime is on the inside. And so we're going to have to solve for the prime. So if we subtract d and divide by c, we find out what x prime is actually equal to. And that gives us that opposite relationship, because we had to solve the x's. Okay, that's about 15 minutes of theory. What's it look like when we're actually trying to make a graph? Let's look at a real graph. Let's say this is the graph of the function f of x. And on this graph, we're going to put on the point -3, 1. We're going to put -1, 3. We're going to put 2, -1. And we're going to put 3, 1. And the way we're going to connect this graph is kind of with a quarter circle looking thing. Then we're going to do a straight line. And then we're going to do kind of an upside down quarter circle. That is the function of f of x. We're going to attempt to graph the function y equals 1/2 f of 2x plus 3 minus 1. The outside stuff around the f of x is going to affect the y coordinate. So our new y coordinate, y prime, is 1/2 of the old y coordinates. That's all that f of stuff minus 1. The inside stuff is going to affect the x-coordinate. And remember, this one we're going to have to solve. X equals 2x prime plus 3. So when we solve, we subtract 3 from both sides and divide by 2 to get the new x prime, the new x-coordinate. So looking at our graph, we were given 4 points. The first point was negative 3, 1. The second point was negative 1, 3. The next point given to us was 2, negative 1. And the next point given to us was 3, 1. Each of these points is going to translate and move to a new location, a new x, comma, y. That is what we are going to find. So first, let's look at the x's. Our formula to find our new x's is we're going to subtract 3 and divide that number by 2. So x's, that first column, negative 3 minus 3 is negative 6. Plugging into the x here in this formula in green at the bottom, x minus 3 over 2. So negative 3 minus 3 is negative 6, divided by 2 is negative 3. When I plug negative 1 in, the second point, negative 1 minus 3 is negative 4. Divided by 2 is negative 2. The third point has an x-coordinate of 2. So I plug that in for our x. 2 minus 2 is negative 1 half. And then finally, my last point is 3. 3 is my x-coordinate. 3 minus 3 is 0 over 2 is 0. What we've done is we found all of our new x-coordinates by plugging them into the x formula that we found. Now we'll do the same thing with the y formulas. Y prime is equal to half of the y minus 1. This might be easier if I have a common denominator. The common denominator here is 2, so if I make that minus 1, 2 over 2, we're going to have y minus 2 over 2. And that way I can just flow through. I could have done this common denominators every time or however, but we're going to work these new y's the same way. So we're going to plug these y's into y minus 2, and then we'll put it over 2. So 1 is my first y coordinate. 1 minus 2 is negative 1 over 2. 3 is my second y coordinate, so 3 minus 2 is positive 1 over 2. Negative 1 is my next y coordinate. Negative 1 minus 2 is negative 3 over 2. And then plugging 1 in for the y, 1 minus 2 is negative 1 over 2. We now have the new points for our graph. We're going to have to do a lot of scrolling here as I do this. The x's, I notice, go from 0 to negative 3. And the y's go basically up to 3 halves. There's negative 1, negative 2, negative 3, negative 4. And there's 1, 2, 1, 2. That's, you can split that into halves. Our first point was negative 3, negative 1/2. So we'll go negative 3, negative 1/2, and there's my first new point. The second new point is negative 2, 1/2. Negative 2, positive 1/2. Here's my next new point. Negative 1/2, negative 3/2. Negative 1/2, negative 3/2. And finally, 0, negative 1/2. These are our 4 new points that we got off of our original 4 points. Now we're going to try and match the shape. We're going to have to curve up, straight line, and curve up. So we're going to match that here. We're going to curve up, straight line, and curve up. We match the shape. And this is now our new function. Our y equals 1/2 f of 2x plus 3 minus 1. This is a process that feels really clunky the first time you do it, but yet the steps are actually really similar. Notice what we did is we identified the parts that affected the y to come up with our y equation. We also identified the parts that affected the x to come up with our x equation. The x equation we had to solve for x prime. The y equation, it's helpful if you have fractions to write it as a single fraction, get a common denominator. And then using those formulas, we took all of our old x's to come up with new x's. All of our old y's to come up with new y's using those formulas. Then it's just connect the dots to get our new graph. So let's try one more before I let you go on the homework assignment. Let's do a real simple graph here. We're going to do 5 points here. Negative 2, 1. Negative 1, 0. 0, 2. 1, 0. And 2, 1. The way we're going to connect the dots is we're going to come straight down on the left, make kind of an upside down parabola looking thing, and then straight up on the right. So it's going to be kind of this symmetrical, I don't know what that's a picture of. That's what it is. We're going to call this the function g of x. I guess I should number this, huh? Let's call this number 2. We are going to find the graph of y equals 3, g of 1/4 x minus 2 plus 1. Again, what parts are going to affect the y-coordinate? The y-coordinate is the stuff around the function, and the function itself is the y. So our new y, our y prime, is 3 times y plus 1. That's going to be a really nice, easy formula for us to use. Times 3 plus 1, times 3 plus 1. Our x's are inside the parentheses. But remember, we're going to have to solve, so it's backwards. X equals 1/4 x prime minus 2. So to solve, we're going to have to add 2 to both sides, and then we clear the 1/4 by multiplying by 4. And you can distribute if you want. I'm just going to do the order of operations, add 2, multiply by 4. Add 2, multiply by 4. And that'll give us our new x-coordinates. So, our points that we're working with are negative 2, 1, negative 1, 0, 0, 2, 1, 0, and 2, 1. We're going to apply these formulas we just found to find our new x coordinates and our new y coordinates. Then we'll be able to graph our new graph. So first the x's. We said order of operations, we have to add 2 and then multiply by 4. So negative 2 plus 2 is 0, times 4 is 0. That's our new x. Negative 1 on the second point, plus 2 is 1, times 4 is 4. 0 plus 2 is 2, times 4 is 8. 1 plus 2 is 3. 3 times 4 is 12. And 2 plus 2 is 4, times 4 is 16. Those are our new x values. The y values, to get our new y values, we plug them in for y in the y prime equation. This y prime equation tells us we're going to multiply by 3 and then add 1. So in the first point, y is 1. 1 times 3 is 3, plus 1 is 4. Try 0. 0 times 3 is 0, plus 1 is 1. Plug in 2. 2 times 3 is 6, plus 1 is 7. Try 0. 0 times 3 is 0, plus 1 is 1. Plugging in 1. 1 times 3 is 3, plus 1 is 4. And so now we have our new coordinates. Notice the x's are going to have to get really big. Everything's in the positive range. So x is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We're going way out there. The y's are going to have to go up as high as 7. So we start plotting our points, 0, 4, 4, 1, 8, 7, 1, 2, 3, 4, 5, 6, 7, somewhere around there. 12, 1, and 16, 4. Then we connect the dots, keeping the same shape as the original function, the straight diagonal, the upside down looking parabola, and the straight diagonal. This now is the graph of y equals 3 times f of 1/4 x minus 2 plus 1. This is the process we're going to go through on these graphs. Every single problem is the same way. You look at the points that we know, and how are the y's going to change? That's what's happening on the outside around the function. How are the x's going to change? That's what's happening inside within the function, and we have to solve for that variable, giving all those opposite operations. Then just go through all our points. Change the x's using the x formula. Change the y's using the y formula. Take a look at these on your homework. You want to get really good at how these graphs move around before we start introducing the basic functions and how we can move those graphs around. If you can master today's lesson, tomorrow will be easy, easy, easy. So take the time to do well, look at the homework assignment, and we will see you in class.